This new research put out by Bhattacharya and Joshi about naked singularities forming in the very early universe is very interesting to me, since I am of the conviction that the Higgs boson event was a naked singularity produced at the LHC in 2012. We think that it's a new particle called the Higgs boson. I don't think that's at all. I think it's a naked singularity because of its decay products, because it decayed into two gamma ray photons, and yeah, that's what we'd expect from black hole evaporations. However, I was reading this Bhattacharya Joshi paper today, and I was very very intrigued by the possibilities that could be presented by future colliders, future particle accelerators, and it may well be the case that future particle accelerators could provide a means of testing actually my theory of quantum gravity, my hypothesis on quantum gravity, because if my hypothesis on quantum gravity is the truth, then microscopic black holes should only be possible to create using atoms as opposed to protons. If you just fire protons together, there's nothing there to create an event horizon. You'll just be creating what's known as a naked singularity. Excuse me. So you can fire as many protons together as you like, all you'd end up with is a naked singularity, which would decay instantaneously into gamma ray photons. However, if you were to fire atoms of one another, i.e. atoms of hydrogen at one another, their electron densities would coalesce into a sort of little black hole with a singularity at the centre formed of the two protons, but it would be shrouded by an electron density. And this electron density would be repelling light, it would also be drawing light into it. Since if a light ray happens to come across an electron density, it of course gets trapped in there, and there's some probability that it will then be absorbed by the particle that it's surrounding. If you were to create a sufficiently dense composite particle, formed of something that already had an electron density, you would thereafter be able to create a small black hole. And these black holes ought to be right, rather safe to deal with, because they evaporate very quickly via Hawking radiation. We would hope, in experimental conditions, in laboratory conditions, where there's perfect vacuum and ideally nothing for them to accrete, except possibly background radiation, background photons, right? So this is how we'd go about creating black holes. And my theory would predict, or my hypothesis, if you like, would predict that the creation of a microscopic black hole would not be possible without an electron density to begin with, without an electron surrounding, i.e. atoms. You need atoms to begin with to create a microscopic black hole, as opposed to a microscopic naked singularity, which I think has already been created, if you see what I mean. So I'm back doing real science, of course, since this is a hypothesis still. I think it's a theory also, because I think it's got a substantial weight in evidence from what we've observed in the universe already. And I think that this is a real scientific possibility that could really be tested in either the Large Hadron Collider that we have at the moment, or in future larger particle accelerators that we're planning on building. Is it the future circular accelerator or something like that they're planning on building? Or the future circular collider? That's it, isn't it? Yes, that one. I suggest we build that. Or maybe even start building particle accelerators in space if we're worried about black holes. I think that might be an even better idea. Just keep it away from the planet a little bit. And I think that's well within our capabilities also. At this point, and it certainly will be within our capabilities in the future, and constructing particle accelerators in space and doing other particle physics experiments in space. I think there's huge potential for space as a laboratory, and getting the muon G-2 experiment up there. That was another prediction of my quantum gravity model, that the muon G factor would accord with the predictions of the standard model in microgravity, since I analysed the results from Brookhaven National Lab and Lawrence Livermore National Laboratory. It's Fermilab and Brookhaven National Laboratory, I think. that I compared the results between, and I think that the G factor is augmented in the results between those two facilities by its difference above sea level, i.e. its varying level of elevation within an electron density. So you have more electrons in the background, creating more special relativistic effects over the muon in the collider, and yeah, it would be affecting its G factor that way, the wobble in its spin that way, and yeah, I think that my idea still is in the game very much, and I think it's very testable, very much testable, very much more testable than string theory is, or seems to be, very much more testable than classical graviton models. So yeah, that's something worth considering. And thank you to Pankaj Joshi and uh, Bhattacharya. I can't remember his first. Sorry, bye.